Hello, everyone, and welcome to the University of Tokyo School of Science Open Campus. My name is Kenneth Wong. I'm a researcher at the University of Tokyo's Research Center for the Early Universe. The title of my talk is The Trouble with Hubble, A Crisis in Cosmology. So in the 1920s, an American astronomer by the name of Edwin Hubble made an important discovery. What he found was that the universe is expanding. And what we mean by that is when we look out at galaxies outside of our own Milky Way, they all seem to be moving away from us. And the further away a galaxy is, the faster it seems to be moving. So one way to think about this is to compare space to a loaf of bread that's rising. So for example, if you have some dough and embedded within the dough are little nuts or something, you can think of the dough as representing space and the nuts representing galaxies. So as the dough rises and expands, it's carrying all of the nuts away from each other. Similarly, as the universe is expanding, it's carrying all of the galaxies embedded within it away from each other. So from the perspective of any one galaxy, all of the other galaxies look like they're moving away from us. And the further away a galaxy is, the faster it's going to be moving away from us. So if the universe is expanding today, that means in the past, it must have been smaller than it is today. And if you go back far enough in time, there must have been a point where the entire universe was extremely small and extremely dense. And from this very small, very dense starting point, it expanded rapidly. And we call the start of this expansion the Big Bang. So the expansion rate of the universe today is a very important quantity. It tells us things about the universe's age, its size, and its eventual fate. So the rate of expansion we call the Hubble constant. It's represented by this H naught, so capital H with a subscript 0, H naught. So how do astronomers measure the Hubble constant, H naught? Well, what Edwin Hubble did when he did his initial observations back in the 1920s is he looked at the speed and the distance of galaxies outside of the Milky Way. And he came up with this law called Hubble's law, V equals H naught D. So V is velocity. This is just the speed at which a galaxy is moving away from us. D is the distance to that galaxy. And H naught, the Hubble constant, is the rate at which it's moving. So this plot here shows some of Hubble's original data. And what we can do is, if you can measure the velocity and distance of these galaxies, you can plot them like this. And the line that they fall on tells you H naught. It's just the slope of this line that all of these galaxies fall on. So this is how we can measure H naught. So in general, in astronomy, measuring velocity is pretty easy. You can look at an object's spectrum. So what the spectrum is you take the light from a galaxy or any other object, and you pass it through something like a prism. And what that does is it breaks the light up into all of the different colors in its spectrum. And when we look at the spectrum of a galaxy, we see, all different colors like this in these examples here. But we also sometimes see these bright or dark lines in the spectrum. So in this bottom spectrum shown here, you see some dark lines. So these lines represent specific elements within the galaxy that we're observing. We know based on experiments we can do in the laboratory that certain elements will have certain features at certain wavelengths of light. So for example, hydrogen has some characteristic, we call them absorption lines, that you can see as these dark lines here. And they happen at very specific wavelengths of light in the spectrum. And similarly, helium will have different characteristic absorption lines, oxygen, carbon, so on. But when an object like a galaxy is moving away from us, what happens is that its light becomes redshifted. What that means is all of its features get shifted toward longer wavelengths, or it becomes redder. So when a galaxy is moving away from us and we look at its spectrum, we can pick out these characteristic lines that tell us what elements are present in the galaxy, but they're all going to be shifted to redder wavelengths than we measure here in the lab on Earth. And it turns out that the amount of the redshift, how much they get shifted to the red part of the spectrum, tells you how fast it's moving. So the faster the galaxy is moving, the more those features will get redshifted. So in this example shown here on the bottom, you see just a laboratory reference. So this is what we would measure here on Earth, just in the laboratory for certain elements. The one above it is a nearby galaxy. You see the lines get moved a little bit toward the red end of the spectrum because it's not moving so fast. And then as you get galaxies moving faster and faster away from us, the lines get redder and redder. And so by observing the spectrum of a galaxy, we can measure its redshift and therefore determine its velocity. However, measuring the distance to objects in astronomy is very difficult. So it's not like measuring distance to objects here on Earth, because you can't go out to other stars or other galaxies and measure how far you went to get there. Instead, we need other methods to measure distances in astronomy. So one particular method that's very useful is called parallax. So to understand parallax, you can actually do a simple experiment right now by yourself. All you need is just take any finger, hold it out in front of you like this, and close one of your eyes. Close, for example, your left eye. Keep your right eye open. Focus on where your finger is. Then close your right eye and open your left eye. And just blink back and forth between your left eye and your right eye. You see how your finger appears to be moving in comparison to the background. That's because the angle that your left eye makes with your finger is slightly different from the angle that your right eye makes with your finger. Now, do the same thing again, but this time, hold your finger closer to your face, and now do the same thing. Just blink back and forth, left, right eye. You see the same effect, but when your finger is closer, it appears to be moving more than when your finger was further away. That's because you've changed the angle. The angle is now larger between your left eye, your finger, and your right eye. So this exact same principle works with parallax. We look at some object like a star, for example, compare it to where it is compared to its background objects. And then 6 months later, when the Earth has moved to the other side of the sun, we look at the same star and we see how much it has shifted compared to objects in the background. And the amount of that shift tells us the distance, because if it shifts by more, that means it's closer to us because that angle, that parallax angle, is larger. If it shifts by only a very small amount, we know it's further away because the parallax angle is going to be smaller. So this is how parallax works. Unfortunately, it only really works for very nearby objects. It works for objects within our Milky Way and a few nearby galaxies as well. So another way to measure distance in astronomy is using what's called a standard candle. So standard candles is any object where all objects of that type have the same luminosity. They always give off the same amount of energy. And this is useful because if we know how much energy this particular object gives off, then whenever we see one, we can tell based on how faint it is, how far away it is. So if it's close to us, it's going to appear brighter, or if it's far away, it's going to appear fainter. And we know that because since it's always got the same luminosity, the same energy output, we know the difference in brightness has to be due to its distance. So I want to talk about two very important standard candles in astronomy. The first are what we call Cepheid variable stars. So a Cepheid variable is a pulsating star. So these are very large stars toward the end of their lifetime that kind of pulsate. They get bigger and smaller over time. So these stars tend to be quite bright, at least compared to most other stars. And we've discovered that the period of their pulsation, meaning like how long it takes to get brighter and fainter, is related to their luminosity. And once we correct for that period, we can solve for the luminosity of the star. We know how much energy it's giving off. So this makes it a standard candle and now we know that when we see a Cepheid variable and we can measure the period of its pulsation, how long it takes to get brighter and fainter, then we know how much energy it's giving off. And therefore, based on its brightness, we can tell how far away it is. Another very important standard candle is sometimes when a massive star dies, it will explode in what we call a supernova. So these supernovae are extremely bright. They can outshine entire galaxies when they go off. And there's a certain type of supernova called a type 1a supernova. And type 1a supernovae, it turns out, are standard candles that once you do a few calibration steps, you can determine how bright they are intrinsically, how luminous they are. And because they are so bright, you can see them to huge distances, and therefore they're very useful for determining distances to faraway galaxies. So what astronomers do to measure distances is we first use something like parallax, something to get us nearby, some distances to some nearby stars in our Milky Way and other galaxies. And using parallax, we can calibrate Cepheid variable stars. So for example, we see a nearby galaxy where we can measure its distance due to parallax. And then if that galaxy has some Cepheid variables in it, now we know how bright Cepheid variables are because now we know the distance and we can measure its brightness, so we know its luminosity. That gets us the intrinsic energy output of Cepheid variables. Now we can use them as standard candles. Then we look a little further out and we find some galaxies where we see Cepheid variable stars and there's a type 1a supernova that goes off in that galaxy. Now we use the Cepheids to calibrate the luminosity of type 1a supernovae. And now we know the intrinsic luminosity of those supernovae. And because they are so bright, these supernovae can be seen to huge distances. Now we can use them to measure distances very, very far out. So this process of using progressively further and further distance indicators to calibrate one another, so going from parallax to Cepheid variables, then to type 1a supernovae, we call this the distance ladder because it's like a ladder with rungs. So the first rung gets you a little bit further away from the Milky Way, that's parallax. The next rung gets you even further away, that's Cepheids. And then the third rung gets you type 1a supernovae, which gets you very far out into the universe. So using this distance ladder technique, we've been able to measure distances to faraway galaxies, and we can measure their velocities using their spectra. So combining these two with Hubble's law, there's been a measurement done by the Shoes collaboration that has measured the Hubble constant H0 to be 73 kilometers per second per megaparsec. So just for reference, a megaparsec is a unit of distance. It's about 3 times 10 to the 19 kilometers. So this is one way that astronomers have been able to measure H0. So one thing about this expansion is that what you would expect is that because gravity is pulling everything in the universe together, it should be pulling massive objects together. We would expect that the expansion should be slowing down with time, because even though it's moving, everything's moving away from each other, due to gravity, that expansion rate should be slowing down and could potentially even turn around and start collapsing in the future. So can we observe this effect? Well, yes, we can. But when we did that, it turns out we were in for a surprise, because not only was the expansion of the universe not slowing down with time, it was actually speeding up with time. So this was actually a huge discovery back in the late 1990s, and it won the Nobel Prize in 2011 because it was such a shocking, unexpected discovery that the universe is actually accelerating, and we have no idea why this is. The cause of this acceleration is still unknown, but astronomers have decided to call it dark energy. Now, we don't know what dark energy is, but maybe we can get some clues about it by looking at the light from the early universe. So this diagram here is sort of a cartoon picture, starting from the Big Bang on the very left, and then how it evolves into matter and then stars and galaxies as you go further in time to the right. But at near the very beginning, near the Big Bang, you see this strange light right here. So if we observe the light from the early universe right here, we can get some clues as to what dark energy is and why it's behaving the way it is. So this light from the early universe, we call this the cosmic microwave background, or the CMB for short. So this is the light from the very early universe just after the Big Bang. So when the universe was very young, just after the Big Bang, everything was so hot and so dense that atoms could not form. It was too hot for protons, neutrons, and electrons to come together and form atoms. Eventually, protons and neutrons came together to form nuclei, but electrons could not bind to these nuclei to create the elements as we know them today. So what you had was this primordial soup, this plasma of nuclei and free electrons. And you also had a lot of light and radiation, but because radiation scatters off of free electrons, the light couldn't just flow outward unimpeded. It kept scattering off of the electrons. So imagine this very early universe, very hot, very dense. You have nuclei, you have electrons, and you have photons of light that are just scattering off of all of these electrons. So as the universe expands, it cools down, and eventually, a few 100,000 years after the Big Bang, it's expanded enough and cooled down to the point where suddenly it's cool enough for atoms to form. So the electrons can now bind with the nuclei and form elements like hydrogen, helium, and a few other trace elements. Now, once that happens in this process we call recombination, now there's no more free electrons in the universe. So all of the photons can now stream freely out in all directions. And these photons, from that point at which recombination occurred, we can still see today, but they've all been redshifted to microwave wavelengths because they've been traveling through space for so long and that space has been expanding. So that's why we call this the cosmic microwave background, because we have to observe in microwave radiation in order to see it. But this light from that very early phase in the universe tells us a lot of information about the conditions in the early universe. So about a decade ago, there was this satellite called Planck, which is shown here. And the objective of Planck was to observe this CMB and look at the pattern of the CMB in the sky. So what Planck observed was this map that you're seeing on the screen here. So you see all the blue and red dots. Those correspond to hotter and colder parts of the sky as mapped by the CMB. So these are actually very small differences, even though the color represents the differences. The difference is actually not very big. It's about 1 part in 10 to the 4 difference in temperature. But we can look at the pattern and we can tell from the pattern of patches of hot and cold spots here what the components of the early universe were. So in terms of energy, mass, things like that. And we can also predict, based on this CMB pattern, what the value of the Hubble constant should be today. So using the Planck observations and doing some calculations, we can predict what H0 should be. But here's the problem. The prediction that Planck made is different from the measurement that the SHOES collaboration made. So the Planck CMB value, the predicted value, is 67 kilometers per second per megaparsec. And what SHOES measured, if you remember, was 73 kilometers per second per megaparsec. And you may think this doesn't seem like that big of a difference. It's about a 9-10% difference. But each method here claims that their uncertainties are about 1 to 2%. So this is actually much larger than can be explained. This discrepancy is much larger than can be explained by the measurement errors claimed by each of these teams. So why is this? Why do they not agree? Is there something we don't understand about the universe? Is there some problem, some error in one or both of these measurements? So in order to resolve this discrepancy, we need other methods of measuring H0. So my research focuses on what we call gravitational lensing. So gravitational lensing is what occurs when you have a chance alignment of some bright background object, which we call the source, and some massive foreground object, which we call the lens. And if you get this chance alignment of the source directly behind a massive lens, like say a galaxy or a galaxy cluster, when we look out into space and see this configuration, because of the gravity of the lensing object, the lens, we can see distorted and in some cases multiple images of that background source. So for example, what you're seeing on the left here is a massive lens galaxy, which is that yellow blob in the middle. That's a massive galaxy. And the blue ring around it is actually a background blue star-forming galaxy, but it's been distorted and warped and lensed into these multiple images that form a ring shape because of gravity. So because of the light bending effect of gravity, we can see these strange configurations out in space. So here's a short animation that illustrates the lensing effect. So light coming from the source gets bent by the lens and gets focused towards the observer. And now when we're going to see a different perspective here, when we look out in space and we see what this actually looks like, we see the lens galaxy with multiple distorted images. Here's an illustration of a lens source where now there's two images, and both of these images are of the same object. So it's like 2 points of light, but they're actually 2 points of light of the exact same object. So we know that the light from those two images had to come from the same location in where the source is, but they took slightly different paths through space to reach the observer here on Earth. So if we see some light from the brighter image, it went around one side of the lensing object, and we see light from the fainter image, it went around the other side of the lensing object. And because that path is slightly different and the gravitational potential on each of those paths is slightly different, there's actually what we call a time delay between those two images. So what that means is that if two light rays get emitted from the source at the same time, one goes through one of the images and the other goes through the other image, they're going to arrive at Earth at different times. So here's an animation showing that. Here's two light rays being emitted at the same time. One takes one path through space, the other takes another path through space, and the path length is a little bit different, one slightly longer than the other, and then the gravitational potential is a little different. So those two effects together create this time delay because those two light rays are going to arrive at different times. So one analogy for this is to think of it like train lines. So for example, let's say you had two trains leaving from Shinjuku Station, heading to Tokyo Station. One's going along the Yamanote line, one's going along the Chuo line. Even if they left Shinjuku at the same time and travel at the same speed, because the path they took is slightly different and they stopped at a different number of stops, so that represents gravitational potential, they're going to arrive at Tokyo Station at different times. So this is analogous to the time delay effect in gravitational lensing. And this is useful because it turns out that you can determine the Hubble constant h naught using gravitational lensing because of this effect. All you need to do is determine what we call the potential of the lens, the gravitational potential represented by phi lens here, and measure the time delay, delta t. So the Hubble constant h naught is proportional to the ratio of these two terms. So got to measure the gravitational potential, measure the time delay, and then you can determine h naught. And this method is completely independent of the CMB and completely independent of the distance ladder. So this is the alternate method we need to check the h naught results. So if the background source is what we call a quasar, so a quasar is just a very supermassive black hole at the center of a galaxy, and it's shining very brightly because as gas and dust falls into it, because of conservation of angular momentum, it spins up very quickly around the black hole as it falls in. And due to friction, it gets very hot and emits very bright light. So these objects are very, very bright. They can outshine even the host galaxy that it's in. And the key thing about quasars is that they flicker on short timescales. So because of this flickering, its brightness is changing over time. So in this image, you're seeing an example of just a quasar on the left and a gravitationally lensed quasar on the right. So you see 4 images of a quasar here. And this is useful because due to the flickering of the quasar, that change in brightness, we can actually measure how the brightness of a quasar is changing over time. But because of the time delay effect, we see those changes offset in time. So this movie being shown here is actually from real data. What we're measuring here on the bottom is the light curve of each of the 4 images of this quasar. So what we do is every night we just take an image of this lens quasar with a telescope, measure how bright each of those 4 images is. And then over time, we plot how bright is each of those 4 images on every night. And we build up what we call the light curve of these objects. So just how bright is each of those objects with time. And whenever something happens at the quasar, maybe it gets brighter all of a sudden or fainter all of a sudden, we see that happening in one of the images first. So in this particular case, you see image B, there's a brightening event that happens. Then we see it a few days later in image A, then image C, then image D. So this offset in the arrival time of photons, the time delay effect, gives rise to this shift in the light curves. And we can determine the time delay of the gravitational lens by comparing these light curves and seeing how much you need to shift them in time to get them to match up. So here's an example of one of our light curves for a gravitational lens. So this is the lens with the images A, B, C, D. And on the light curve above, you see just the results of, this is 13 years worth of monitoring. So for 13 years, just every night or every few nights, measure the brightness of each of the 4 images and just plot them over time. So you see these features. There are some dips, some peaks, and you just want to solve for the offset in time that you have to shift these curves by to get them to lie on top of one another. And that tells you the time delay of the lens. Okay, so that's one of the 2 pieces we need to determine H naught. So the next piece is this gravitational potential phi lens. So when I showed you this image earlier, it's actually a little bit misleading because this image on the left is not actually the de-lensed image of the lens on the right. So these are 2 different objects. And the thing is, you can never observe the true source because the lens is in the way. You can never move the lens and get at what the source actually looks like. All you can do is estimate what the source looks like based on modeling. So what we want to do is, to get the gravitational potential, we need to determine how much mass is in the lens galaxy and then calculate the potential from that. So how do we do that? So we know that the light that we see at each of these 4 images here, they have to come from the same location in the source plane, that bright background source. It has to give rise to these 4 images. And we can ask the question, how much mass do we need to put here in the lens galaxy so that when we reverse the lensing effect, all of these 4 images get mapped back to the same location at that background source? So we can build models and solve for that quantity. So we want to determine the amount of mass we need here at this lens galaxy to reverse the lensing effect and get everything to match coherently. And from this mass, we can then determine the gravitational potential of the lens. So to do this, we need very high resolution data. And we get that by using the Hubble Space Telescope and eventually the James Webb Space Telescope. So we need space telescopes because they're above the atmosphere. So the Earth's atmosphere can cause blurring and distortion in our images. We want very, very high resolution to get detailed images to build our models. So we need to go to space for that. We need the Hubble Space Telescope or the James Webb Space Telescope. So once we have that data, we can then try to model and predict the amount of mass we need to reconstruct our observations. So here's an example of a gravitational lens. The top image shows the actual data. So this is a real lens using this image from the Hubble Space Telescope. The second image just below it is our model prediction. So this is our best model reconstruction of the image. We want our model to be able to reproduce the data as best as possible. You can see by comparing these two, it's a pretty good match. And then from our model, we can determine the gravitational potential, and we can even predict what we think the source will look like. So remember, I said you can never observe the true source, but the bottom panel here is what our model predicts the source should look like if there was no lensing effect. So from that modeling, we can then determine phi lens. So now we have the two pieces we need. We have the gravitational potential from the Hubble Space Telescope imaging and our modeling, and we have the time delay measurement from monitoring the lens quasar and getting the light curve. So when we put these two together, we can now determine the Hubble constant. So what do we get? So our latest results show that from the combination of 7 gravitationally lensed quasars, our collaboration called TD Cosmo has measured H0 to about 2% precision. And what we find is a value of 73.7 kilometers per second per megaparsec. So here we're comparing what was found by the Planck CMB result. So that was about 67. And the Shoes distance ladder result, which was 73. So our result from TD Cosmo is more in agreement with the Shoes result than it is with the Planck CMB result. So why is that? Why this discrepancy? Well, we don't know yet. There are a few different potential answers. The most boring answer would be some sort of systematic error. There's some problem with some of the measurements. Maybe the Planck measurements are wrong. Maybe our measurements are wrong. We've overlooked something. Maybe the Shoes measurements are wrong. They've overlooked something. We can't completely rule that out, but now we have 2 measurements that agree. So that maybe provides some more evidence in favor of the higher value. However, at this point, there are also a few other methods of measuring H0 that also don't seem to agree. So I'm just going to list a few here. So I will say that at the moment, none of these seem to be as precise as the ones I've shown. They're not as precise as the CMB, the distance ladder, or gravitational lensing. But these other methods do exist. And when you kind of look at them and sort them out, there's not really agreement. But what we do notice is that you can sort the different measurements into what we call early universe and late universe measurements. So early universe being, for example, CMB measurements based on observations taken just after the Big Bang. So Planck is one such measurement. That's why they got a low value. You see all the early universe measurements tend to get a value around 67, 68. And other measurements can be classified as late universe measurements. So these are more local, more direct measurements of the expansion rate, H0. So the Shoes distance ladder result falls into this category. So does the TD Cosmo gravitational lensing result and a few of these other methods that I've shown here. And you see that most of the late universe results are getting kind of a higher value around 73 or so. A few higher, a few lower, but broadly speaking, there seems to be this divergence between early universe and late universe measurements of H0. So aside from potentially systematic uncertainties, there are a few other potential explanations that could be more interesting. So one possibility is that the universe is more complicated than we think. So we have sort of a standard model of the universe that seems to fit most of the observations quite well, but maybe there's some additional mass or energy component in the early universe that we're not accounting for. Maybe there's some early form of dark energy that we're not accounting for. Maybe dark energy is changing over time. That's another thing that has been proposed. We're not sure yet. We still need to confirm a lot of these measurements. People are coming up with new ideas all the time and coming up with ways to test them. But until there's a resolution to this, this is going to be a huge topic and is a huge controversy in astronomy at the moment. And it's even been in the news quite a bit. If you look at some popular science outlets, they've been reporting on this so-called Hubble tension. And as for the TD Cosmo collaboration, we're going to continue to analyze gravitational lenses. We're going to continue to look for new lenses to add to our sample to get a more precise measurement of H naught and hopefully shed more light on this discrepancy. So thank you very much.